Okay, today we're going to look at Newton's third law, and Newton's third law is a little bit different than the first two because the first two are talking about the force that's acting on one object. So law of inertia, the first law, is an object will stay at rest or continue in motion unless there's an unbalanced force acting on it. Newton's second law was we do have an unbalanced force acting on an object, so that's going to cause it to accelerate. Now, Newton's third law is a little bit different because it's talking about two different objects interacting with one another, and his law states that every action force has an equal and opposite reaction. So what that means is if you have two objects interacting with each other, the force of object A acting on object B is going to be the exact same as the amount of force on A from B. So in the diagram you see here, I got two boxes A and B. A is pushing against B, B is pushing against A. Those two forces are going to be the same, and that's what his law is talking about. A key thing to remember is, even though the forces are the same, it doesn't mean they cancel out. So what we're talking about here is we don't just have one object, and we have a force going one way and another force going the other way. Okay, so that would be like Newton's first law or second law, so those would cancel, the object wouldn't move or wouldn't accelerate. Okay, so we're not talking about that situation here. What we're talking about is we've got two different objects. One's pushing against the other one, so the other one has a reaction force going the other way. And because those things are acting on different objects, even though the forces are the same, it doesn't mean that motion won't occur. It just means that they're going to occur differently. So because they have different masses, if you have equal forces, the masses are going to then change how much acceleration each one has. So let's just do a simple example. So let's suppose we have our two boxes A and B as shown above, and let's suppose, imagine it was two people on ice or two people sitting on skateboards or something like that, and they push against each other. So the amount of force will be the same. Each one's going to go off in opposite directions. So the question is, if person A is 10 kilograms and it accelerates to the left at -2 meters per second, B then will have a mass of 7 kilograms. We want to calculate what its acceleration would be. So it'd be just like the diagram I have above. A and B are different sizes. They're going to go in opposite directions. The forces will be the same, so this force will equal this force, but the accelerations will be different because they have different masses. So all you have to do is calculate the force on A, calculate the force on B, and solve them. So mass times acceleration of A will also equal mass times acceleration of B. So 10 times -2 will equal 7 times whatever its acceleration would be. So we'd have -20 equals 7A. We don't really have to worry about the negative because we know they're opposite directions anyway, and that's all the negative is telling you. So if you go 20 divided by 7, that gives you an acceleration of -2.86, and the negative, like I said, just going to mean opposite direction. Okay, so quite often with these ones we'll just ignore the negative signs because we know that originally the negative just meant it was going to the left. Obviously B is going to go to the right. Okay, so you can see then the lighter object's going to have more acceleration, the heavier object's going to be less, which totally makes sense. So what we're going to look at next is kind of an interesting example. So we have an apple falling to the earth. So let's suppose the apple is 0.15 kilograms, and it's going to fall to the earth. And then the question is, if the apple accelerates downwards to the earth, how much is the earth going to accelerate upwards to the apple, right? If they have equal and opposite reactions, that means the earth is pulling the apple down, but the apple's also going to pull the earth up. So we'd have an apple that's 0.15 kilograms. So that'll be the mass. Let's call this apple. And the mass is 0.15, and we know the acceleration is gravity, 9.81. And let's do the earth. So the earth has a mass of, we have this in our formula sheet, it is 5.97 times 10 to the 24 kilograms. So the question is, what's the acceleration of the earth? So if we do the same thing we just finished, mass times acceleration for the force of the apple, that has to equal the force of the earth. So that'll be mass times acceleration of the earth. So we'd have 0.15 times 9.81 will equal 5.97 to the power of 24 times a. So if we multiply those out, divided by 5.97, we will get an acceleration of 2.46 times 10 to the negative 25. Okay, so the question is, we drop an apple, it falls to the ground, we see it drop because it has a light mass and an acceleration of 9.81. So when you multiply those, we actually only get a net force of about 1.4 newtons. So that's pretty small force, right? 1.5 newtons, pretty tiny. So that amount of force to move the mass of the Earth is not going to do very much. So an answer to the negative 25 means we have 0.0000025 zeros, or 24 zeros, and then 2.46. So that's pretty close to zero, right? It's such a small number that we'd say it's pretty much zero. So the Earth pulls the apple down with 1.5 newtons. The apple pulls the Earth up at 1.5 newtons, but because the mass of the Earth is so large, it's basically negligible, and we'd say zero. Okay? So we get the idea with questions like that. The next example I want to look at is one where you actually have to use one of the old formulas. So for example, if we have, let's suppose we have a bullet getting shot out of a gun. Okay, and we know the bullet has a mass of 15 grams. So be careful, you got to change that to 0.015 kilograms. And we know it gets shot out of a gun. It says the rifle has a gun mass of 6 kilograms. And the other thing we know is that the bullet travels 75 centimeters as it leaves the gun. So that'd be 0.75 meters. And we know that it has a final velocity of 70 meters per second when it leaves the gun. Okay, so the other thing, we can assume that it starts at 0, right? Before the bullet gets shot, it has a VI of 0. So that's it. So you can see, to do this question, we're going to have to figure out the acceleration of the bullet. We want mass times acceleration to get the force on the bullet, but we need to calculate the acceleration first. So if we use VF, VI, we got a distance, we can calculate the acceleration of a bullet using our VF squared formula. So we'll do that first. So VF squared equals VI squared plus 2AD. So we'd solve that. We have 70 squared, 0 squared, 2 times A times 0.75. Rearrange that, solve it for acceleration. We get 3266. Repeating, meters per second squared. So now we can actually figure out what the force is acting on the bullet. So the force of the bullet will be the mass, 0.015, times the acceleration, 3266. And that gives us a net force of 49 newtons. Okay? So that means the gun is going to push the bullet at 49 newtons. So that means the force acting on the gun is going to be the same. It's going to be 49 newtons as well. So we'd have 49 newtons will equal 6 times acceleration. So 49 divided by 6 gives us an acceleration of 8.2 if we round it off. Okay, so you can see the concept here is we calculate the force of the bullet, its mass times acceleration. We know that Newton's third law tells us that the reaction force will be exactly the same, so we know it's 49 newtons as well. So if we go 49 divided by the mass, we can calculate the acceleration of the rifle. So the rifle is going to get kicked backwards at 8.2, so you can write it as backwards or negative or however you want. So the bullet's getting shot forward at an acceleration of 3266, the acceleration of the gun 8.2. So quite a bit less. Be enough that you'd feel the kickback of the gun, but not enough to hurt you or knock you over. So you can see that the idea is the gun, small acceleration for lots of mass. The bullet was lots of acceleration, but only a really small mass. But those two forces, once you multiply the two, those two forces are equal. Okay, so it's not so much the amount of force, it's the amount of acceleration that would be the key idea to this case. All right, so the other kind of question, let's do one more. The other kind of question you got to be careful of, again, is what happens if you have two boxes being hooked together with a rope. Okay, so let's suppose we have a box that's 10 kilograms, we have another one that's 5 kilograms, and we're going to pull these boxes with an applied force of 30 newtons. So the question is, what is the tension on the string? So we're looking for the force of tension on the string that's in between the two boxes. Okay, so the first part we'll look at it is if there is no friction. So if we have no friction, then that means our net force then is 30, right? We only have the 30 newtons, and therefore we know the combined mass of the two is 15 kilograms. So our acceleration will be 30 divided by 15, which is 2 meters per second squared. So both boxes will accelerate at 2 meters per second squared. So now we can think of what is the tension on the string. Well, the 5 kilograms is pulling the box to the right. So the tension on the string will be the reaction force. So what you want to do then is calculate the force of just the 10 kilogram box. So you want to picture just the 10 kilogram box. If we have a force of or an acceleration going to the right of 2 meters per second, then our net force would be just mass times acceleration. So you'd have 10 kilograms times the 2. So that would give you a net force of 20 newtons. And that would be our tension on the rope. The 20 newtons is the tension on the rope. Okay, so you can see that works fairly easy. You just got to remember to only use the second mass afterwards. So we're looking at, what is that pressure of the rope as it's getting pulled to the right from the box. Okay, the only other case with these ones that gets a little bit tricky is if you have friction involved. So let's suppose we have a force of friction of 5 newtons backwards on that box and 2 newtons backwards on that box. Okay, so now you can see that we'd have our net force will be 30 plus the negative 5 plus the negative 2. So we'd actually have 23 newtons for net force. So our acceleration will be 23 divided by the 15, which gives us an acceleration of 1.53. Okay, so now for the second part, the tension on the rope. So we still have an acceleration of 1.53, so that part's good. We still have a mass of 10. The difference is this time is you also got to worry about the friction. So this box is also getting pulled back with a tension of 5 newtons. So we have to go mass times acceleration. So we got 10 times 1.53. So that's the net force in this case is going to be the applied plus the friction. Okay, so we have it moving at 1.53, so that means that would be our mass times acceleration there. So we'd have 10 kilograms times the 1.53, and our friction was 5 in the negative direction. So if we solve that equation, then our applied force is 20.3 newtons. Okay, so in this case, the tension on the rope is still going to be 20. So even though that we're pulling this thing with friction, it's going to move a little bit slower, but when you combine all those forces, we still get basically, right, we're going to have to pull it with 20.3 newtons, which would be equal to the pressure on the rope. So our tension on the rope would be 20 newtons if we round it off again. So you kind of see how those ones work. There's a couple practice questions sort of like this. So I'll stop there and you can give that a try.